Sorry. Okay. So this one. Okay, I'm gonna move on. Now, so previously, so far we just covered the single y, scalar y, and now we can actually generalize it to vector y's. And then question is whether we have, so how the missingness is realized for y, and you can think of the response indicator function for y ij by using this notation. So we allow that. Okay. So you have a yij. So j equal to 1 to p. So j becomes a column, right? I becomes a row. So I is I equal to 1 to n. So this is your data, right? So each column represent the item, right? Each row represent the unit. Okay. So then it's very tricky because then, you know, we can have a missingness, something like very, you know, many different patterns, right? We can have all kind of missing structure. So you can see that this is not really well. That is quite general setup. Then here we're gonna introduce some notation. So this notation represent. So this is more like a notation. Basically, the observed part and missing part of the p-dimensional vector, respectively, y obvious and miss. Okay, so for example, p equal 4, y1, y2, y3, y4. Okay, and delta 1, delta 2, delta 3, delta 4, and this is 1, 0, 1, 0. Then y obvious will be y1, y3, and y miss will be y2 and y4, right? So that's for one single realization, and for different unit we may have a different pattern. So then to be rigorous, actually y obvious is depends on I. To be rigorous, because the missing pattern, right? So this is one particular row. Even if you suppose you have a four dimension, and for each row, sometimes you have a different missing pattern. So that means actually for each unit I, this vector actually may change for different row, right? And so to be rigorous, we have obvious I and MIS I, but conventionally we don't use subscript I again, just for simplicity. Okay. So then, how to write express the observed likelihood? So observed likelihood is written by computing the marginal density and the marginal density of your data. So basically you can view this way. For each I, originally you have a delta I. So now this is a vector, delta I and yi, right? But yi is now has a two component, y obvious, I obvious, and I miss. right? Observed part and missing part. So you always observe delta, right? You always observe y observed, and you always missing y missing by definition. So then the marginal density, you can think it is joint density and integrate out over the missing part. So it's just computing the marginal density, you can see that. And then what I mean by this, well, if there's no missing, so if y miss is empty set, y miss is empty, then there's nothing to integrate out. Okay. What does so remember for scalar y, we wrote this way, right? We always delta equal to 1 and delta equal to 0 separately, and then have a different form. And how can we use a single form to express this object likelihood? So actually this expression here, I should. Okay, so this expression here is just a special case of the general expression. Here, so this is a general, but okay, well, actually we have it here. Okay, so well, this is a general expression, and for scalar y, we can write it this way. Why? Because if this is empty, that means you have nothing to integrate out. So then you have a joint, which is this one. Okay. If this is not empty, scalar y, you have a missing for y, then we need to take the integration over y. Okay. So that is the object likelihood. And now if you, so the problem with this object likelihood is that you are interested in estimating zeta, right? Zeta is your parameter interest. And so you using the data you want to basically maximize zeta, and you want to solve this. Maximize this. But the problem is, if you solve this, it depends on unknown parameter phi, which is not really pleasant, because this is unknown, phi is unknown. So question is, Rubin. So Professor Dan Rubin was very interested in this kind of problem, and he came up with some idea. Motivation is that what is the minimum possible assumption that we need in order to solve this without worrying about phi? Okay, without having to. So because this is a function of zeta and phi, right? The problem, zeta is what we are interested in, so this is okay, right? I mean, solving for zeta itself is okay. The problem is that this is not. This is more like a nuisance parameter. So he wants to get rid of this one some way. And question is how, right? What is the assumption we can guarantee to ignore the dependence on phi? So that is the concept of missing a random. Okay. So here's the setup. So so remember, this is bold. So this is a vector. But anyway, this is the conditional distribution also. This is about the missing mechanism. And this is our, definition. And the response mechanism is called missing and random. If probability delta y1 equal to y delta given y2 for all y1 and y2 satisfying. So what does that mean? So this may look ugly, but it really means the response mechanism depends on y only through y observation. So what does that mean? Okay, so if you write it this way, so you decompose original y into the observed part and missing part. And then if you use the Bayes theorem, so this is just the Bayes theorem, right? So this is Bayes theorem. And if this one depends on y only through y observation, that means this under MAR, this guy can be removed. Okay. That means the numerator and denominator cancels to each other. That means what? This is just the two random variables to y, and this you can think of it as a y1 and y2, right? Two random variables. So this is the conditional model of the two random variables. This is the conditional model of the two random variables given the delta. So this assumption basically make your modeling much easier. So the left side you need the modeling for delta, but right side you don't. You don't have to. So basically, this is another way of saying missing a random, or this is another way. So this notation is more like orthogonal. I mean independent. So mathematically means orthogonal means statistically independent, right? So you can think of three random variables: y observed, y miss, and delta. So you can think of three random variables, and the y miss and delta is independent given observable variable. That is the basic concept. So that's another way of saying why. Well, this is in the beginning. I was also when I was a student, I was very confused what really means. As we move on, you will be more comfortable. But for now, I'm going to just introduce the concept and then move on to example, so that you guys feel better. Hopefully, feel better after I cover the example. So some terminology. Missing complete at random. So that is a Lubin's terminology. Missing complete random. Basically, completely. So completely means, like a Bernoulli. I mean, doesn't really depends on anything. You can treat your data, observed data, as if a simple random sampling. I mean, random sampling at all. And missing random is this one. Non-missing random is the most tricky part. And this is the most important result. I mean, critical result. And basically the idea is, so what is this one? Remember, if you go back to the example here, okay, something like this, okay, observed likelihood. So as I said, the observed likelihood depends on not just on theta, but also depends on phi. right? And here in the first term, theta and phi are product, so they can be separated here, but here they don't. They cannot be really separated because of the integration, right? But end of the day, this Rubin's usually says you end up can be partition this way. Then why this is useful? Because if this one holds, then if you take the log obvious theta and phi, then log L1 theta plus log L2 phi, right? And then you take the partial derivative. Okay, then what? This term is 0. Right? So the phi function of phi in the partial derivative differentiated with respect to theta becomes 0. So really, when you are mainly interested in computing the MLE, right? That's something like the estimator of this optimal likelihood. And end of the day, the message here says that you don't have to worry about this guy, second term, and just maximize the first term, which is nice. That's actually, right? That's the original motivation, right? So MLE of theta can be obtained by maximizing L1 theta. Okay. The proof itself is not, so let me briefly use this example to explain the meaning and then go back to the proof, okay? So this is very typical setup. You have a joint PDF. And this one is actually parameter by theta. F1, y given x, and theta. So you are interested in estimating theta mainly, but you have a missing data, okay? So x is always observed, but y is subject to missingness. Okay, you have a fully observed covariate, but y is subject to missingness. So because of the missingness, you have a model. So for example, logistic regression model, something like that, okay? And then how many parameters do we have so far? Well, theta, phi, and also alpha. Why we have so many? Because we have a 3 random variable, essentially. X, Y, delta is written as a marginal of X, and then Y given X, and then delta given X and Y, right? You cannot really avoid this. So once you have this, you need a parameter. So you need a alpha to denote this marginal distribution, theta to characterize the conditional distribution, and phi to characterize the another conditional distribution. Okay, but what we can actually we have a different level of the interest. We are mainly interested in estimating theta. Okay. And this is kind of noiseless parameter in the sense that this model is what we use in order to solve the problem, right? Okay. So, okay, here's an observed line. So, delta equal to 1, remember, delta equal to 1, we observe everybody. So we have joint. Okay. Delta equal to 0, we miss y. So we use the joint and then integrate out over missing data, which is y. Okay, so that's it. Now, so that is just the observed likelihood, and then see whether we can simplify. And we are lucky in the sense that we can have what we can find a term which has nothing to do with the y, right? So the integration is with respect to y, but this F2 term is free of y. So it can go outside the integration. Okay. So that we can factorize. So this L2 alpha is just the marginal density. Okay. So that is actually a good news because even if right, I mean this is why. So good news is that the marginal distribution of X is totally unimportant. I mean, we don't, when it comes to estimating zeta, okay, we don't really need to know the marginal distribution. That's actually the usual setup in the regression, right? If you do regression, you are interested in regression of Y on X, and you don't really specify the marginal distribution of X at all, right? Because you know they can factor mainly because they can factorize your data X and Y, right? As a joint density can be factorized into marginal and conditional, and the parameter in conditional has nothing to do with the parameter in the marginal. So that is basically the reason. So which is nice. And now you can do further. This is actually interesting part because if this probability over delta equal to 1 given X and Y, so this one is actually what is equivalent to 2 delta and Y is conditionally independent on X. Missing mechanism does not depend on the variable. So that is actually missing a random. Okay. And so in the missing and random, that means, so with this guy disappear, right? This guy moves outside. And now in the missing and random, this one doesn't depend on Y. So MAR means you can remove dependency on Y here. That actually is very good because then this guy has nothing to do with the Y integration. So this guy can go outside the integration. Then the only thing left over is just F1 and integration over dy, which is equal to 1. So that actually gives a very interesting result. So you can factorize. First of all, that is actually what the theorem, Rubin's factorization theorem. So the theory here, theorem 2.4, like the factorization theorem, this theorem 2.4. Okay. So basically this one matches with the theorem 2.4. That's good. And another important message here is that because originally we had this guy, and the integration of f1y xi dy, which is equal to 1. Right? So what does that mean? So this one actually doesn't depend on zeta, right? Has nothing, so free of zeta. So that means we can just use this guy to to obtain the MLE. So basically, on the MAR, the MLE of zeta can be obtained by maximizing the first one, which is obtained by ignoring the missing part of the data. So that is sometimes called, so the ignoring the missing part of the data is called complete case analysis.
Because you are using a function like complete cases and you just ignore all the.
Yeah, right. So the default option in R what says is this guy.
Oh, okay.
And the theory here basically says that that is not bad. Actually, that's the best one on the MAR. So that actually confirms is a kind of a good news for us, because what we are doing, what we have been doing so far is not totally wrong, some sense. Okay, but on the MAR condition, of course, but still, this is really good news and useful, because that means actually the MLE, you don't have to, make a very complicated, modeling error. As long as MAR holds, then complete case analysis perfectly gives the best solutions, which is the good news. Okay, thank you for, this is all for today. We'll continue next week. I mean, not next week.